power without becoming angry or afraid. Thank you very much. And now I'd like to call Dave Coulter to the stage.
So I'd like to tell you a story of how we obtained the first ever visible light picture of a gravitational wave source. And that story begins at a prospective dinner for newly admitted graduate students to the astronomy department. So I was admitted, and I was interacting with the other students and the faculty, and I see Ryan Foley. I didn't know that at the time, across the room, and I introduced myself, and I say, "Hello, what university are you visiting from, and are you planning on attending UC Santa Cruz?" And he puts his hands up and he says, "You have it wrong, I'm actually a professor." To which I chuckle and I say, "Yeah, me too." So I tell that anecdote because for me it's emblematic of our relationship ever since then. And I think that there's something that informs that. It's my path to how I got here. I myself was a student of the humanities. 15 years ago, I got a degree in history, took a left turn, learned how to program computers, and then worked in the software development industry for about a decade. In that time, I wanted something more, so I went to night school, got a degree in physics that eventually prepared me for a course of study at UC Santa Cruz. So when I met Ryan, I saw a peer as opposed to a professor. But little did I know that he is an expert observer when it comes to supernovae. So supernovae, they're the massive stellar deaths that produce remnants, and he studies these things. He studies their physics, he studies how they relate to the universe at large. What can you say about the fate of the cosmos and about its contents? And so through talking with Ryan, I became inspired to be an observational astronomer myself. He obliged, and he sent me, before graduate school even started, to Las Campanas Observatory in Chile. So get this, I am a new student, and I am told that I will go to Chile to work on the SWOPE telescope here for 10 nights. And these are winter nights in the southern hemisphere, so they're 15-hour days, or 15-hour shifts, really. So I'm there with my first introduction to astronomy using this telescope, the SWOPE telescope, a 1-meter telescope, for 150 hours. So it was pretty grueling, but right away it let me know, do I actually want to be an observer? And the answer was yes. And furthermore, it gave me this really rich physical understanding of what it meant to observe and how to conceptualize that process, which comes into play later on in the story. So I get back to Santa Cruz, and Ryan floats this idea. Why don't we hunt for the optical light counterparts to gravitational wave sources? That's a big statement, and what I want to do is unpack that a little bit. So I'm going to take you to the state of the art in astronomy thousands of years ago. And that's looking at the night sky and observing. So this was the state of the art for thousands of years, to look, to make careful observations, and it didn't really get more sophisticated until the 17th century, when Galileo turned his telescope to the heavens. When he did that, he saw the moons of Jupiter. He saw the texture of the moon as actually being mountains and craters, and there's topography. So it was surprising. Ever since then, we've been building bigger telescopes that can see deeper into space, which means we can see further back into time. And we even see colors now, colors that we can't see with our eyes, X-rays, radio waves. And that's pretty much how astronomy was, until about the beginning of the 20th century, when there was a glimmer that it could be different. And that came with Einstein. Einstein is most famous, probably, for his equivalence of mass and energy, but he's also equally famous for his conception of what gravity is. He posited that gravity is actually a curvature of space and time. So you can see this animation, this test mass moving around, changing the grid. So he thought of gravity as a curvature of space and time, and part and parcel to that theory are that gravitational waves should exist. So what are gravitational waves? Well, gravitational waves are the literal stretch and strain of space and time itself. And we ought to be sensitive to these things if we only had a good enough detector. And in fact, it was almost 100 years after their prediction that we did detect them with the LIGO detector. Now, this is incredible that we not only confirmed Einstein's theory, but also with incredible precision, we're able to measure distances to 1,000th of a proton to be able to get this detection. And for that, LIGO scientists received the Nobel Prize. But black holes aren't just a clever name. They're black for a reason. They're so massive, they're so dense that light can escape. So as an observational astronomer, I want something else. And neutron stars can offer that. So I mentioned earlier that Ryan was an expert with supernovae, and supernovae, they leave behind a remnant, and in this case, neutron stars. A neutron star, then, is the core of a massive star, and it's composed mostly of neutrons. And so we're talking about something the size of a city that weighs as much as the sun. And as these two objects are orbiting each other, they're bleeding away their orbital energy in the form of gravitational waves. And so as they get closer and closer and closer, they start to rip each other apart and spill their radioactive guts into space. And that produces this sort of emission that we call a kilonova, and that's what we expected to see if we ever did detect merging neutron stars. So there's a catch. If you guys will do me this solid, close your eyes, hold your hand in front of your face, and snap. Now put that above your head and snap. You can tell it's a little bit difficult to see where that sound is coming from. In the same way, LIGO detects like an ear. And so when LIGO detects these gravitational waves, you see these big air regions superimposed in the sky, and they can be hundreds of square degrees. For instance, this September 14th, 2015 region is about 230 square degrees in the sky. So basically, LIGO is saying, we detected something, we think it's over here. Right? So how do we find that as astronomers? To put this in perspective, the full moon is 1/4 of a square degree. So if I shrink this full moon on the scale of those regions on the map, well, you're not going to see it, because there would be almost 1,000 full moons that could fit into that September 14th, 2015. And the story gets a little bit richer. There's a David and Goliath aspect to this, because some of the major collaborations that are looking for these signals are actually spanning a dozen institutions, and they have huge telescopes, and they have hundreds of scientists. And to kind of put that into a visual, here's the Blanco 4-meter telescope compared to the Swope telescope, that red square. So we're talking about the Blanco telescope having 16 times the light collecting power and 12 times the field of view. So they're roughly getting 200 times more photons or packets of light than Swope is. So how can we compete with that? Well, like David versus Goliath, we compete with that with agility and cleverness. So in particular, our collaboration is called the 1-meter 2 hemispheres collaboration, and it consists of a telescope at Lick Observatory in California, and that's associated with the University of California, and the Swope telescope in the south that I already mentioned. In addition, instead of brute force imaging that entire region that we saw, which would pretty much be a fool's errand with a, looking through a straw telescope, instead we're going to target where most of the mass is. We're going to target the galaxies, and it turns out that the universe is clumpy. So we can make intelligent decisions about where to look as opposed to just mowing the lawn, as it were. So it took me about a year to put together this idea in the form of software tools and an actual protocol that we could follow if LIGO sent us an alert. This is an image of the Niels Bohr Institute in Copenhagen, Denmark. So about a year after my time in Chile, this last August, Ryan and I found ourselves at the Niels Bohr Institute at, serendipitously, this basically workshop for gravitational waves. Now, I was there in a different capacity, doing my own research, and we worked like dogs for a few days, and then we took a holiday. So Ryan decides to go to Tivoli Gardens with his girlfriend, and I decide to go to the Louisiana Museum of Modern Art. So, ticket in hand, walking out of the door, the universe had different plans. So as I was walking out of the door, I received an email from LIGO saying that there was a new detection. And not just a new detection, 2 neutron stars. Okay, this is the holy grail detection. And it had a false alarm rate. So the way that LIGO quantifies how much they believe their detection is by describing it in terms of a false alarm rate. This false alarm rate was 1 in every 10,000 years. So 1 in all of the civilizations of Egypt combined, did they think that they were wrong? In addition, we can see here on the top data from the Fermi telescope, which is a space-based gamma ray detector, and LIGO on the bottom. So prepare yourselves. You're about to hear a gravitational wave and a gamma ray burst. On the bottom, you can see this crescendo in cyan, which is the LIGO detection. And believe it or not, that's actually what a gamma ray burst sounds like. So this is so extraordinary because I had just gone to a lecture where Ryan told me that it was unlikely in the next decade that we were going to see a gamma ray detection associated with a gravitational wave detection. In fact, we might not even see it in our lifetime. So this is absolutely bananas. And speaking of bananas, here's the yellow banana that corresponds to the LIGO uncertainty region. Now, I made this analogy between our hearing and how LIGO detects things. Well, it turns out that there was also another detector called Virgo in Italy that had a hand in this detection. So imagine having 3 ears, you'd be able to triangulate things much better. So because of this, we went from hundreds of square degrees in uncertainty to about 30 square degrees in uncertainty, which is definitely a tractable problem with the 1 meter telescope. Okay, so all of a sudden, the race is on. About 60% of the world's astronomers are all looking for this thing at the same time. And where am I? I'm in Copenhagen without phone service, and my boss is on a date. So I text him. Stop what you're doing, please. There's a neutron star detection. I give him the spiel about 1 in every 10,000 years. There's coincident neutrinos, gamma ray burst. And he says, this sounds like a joke. So we go back and forth, and I'm trying to implore him, convince him, with reasoned arguments that this is actually a real detection. And in the process, I'm making hamburger of my coordinate transformations, and he thinks that I'm just messing around. So it gets colorful, so I apologize for that, but you have to understand the moment. And it ends with a supplication that finally does change his mind. So Ryan comes to the office. And by this time, you know, the sun has set and moved on from Africa, and now the night is creeping across the Pacific Ocean, and we're waiting for night to fall in Chile. So we've got 10 hours before we can even start looking. But what I want to draw your attention to here is a sky map from the perspective of the SWOPE telescope. The shaded region you see is actually below the horizon, so there's no hope for SWOPE to see that. And the red little gash on the side, that's the LIGO uncertainty region that we want to search. And if you look at this red arrow, and it's moving from your perspective to the right, the whole map is going to translate that way over time. And really, we only have an hour to look for this thing before it dips below the horizon. So, okay, we waited 10 hours. We furiously were putting together observation lists. I was taking all this knowledge that I had gained over the year of building this pipeline, and we had an hour to find it. And you can imagine there was an intensity, there was a fervor to trying to get everything together. So the situation is we have astronomers at Santa Cruz that are actually receiving the data from the telescope, reducing that data and comparing it with archival information to see, hey, is there something different? And then we also have me and another graduate student and Ryan in Copenhagen actually at the Nerve Center typing things to people in Santa Cruz, but also communicating with the observers in Chile to make sure that they observe things in the right way. And so I just want to prepare you for a lot of motion right now as our chat log goes forward. So this is us chatting, bundling targets together, downloading data, and this is Charlie, who is in Santa Cruz saying, okay, nothing in this field, nothing in field 12. And then here you go. This is the moment, I think, when the hairs on the back of my neck stood up. Found something. And you can see that I'm speechless. It's just an exclamation point. I've lost the words, and in some ways, I still don't know how to accurately describe the feeling. And I think the best visual I have for communicating to you what the feeling is like is an image of my daughter that I just had a couple months ago. So this is her. And she still makes this face when I recall this story and I tell her how I messed up my coordinate transforms. So here we are. Charlie sends us this data here, and this is the before image. This is the image before our image. And then he sends us this. And that might have been hard to see, but there actually was a point of light there that showed up in that image. So I'll make it bigger for you guys. So here, this is the discovery image of a new kind of astrophysical transient. And it's easy to see which one of those points is the actual object because, well, one second. Because there's a red arrow. Okay, but in all seriousness, this archival image, we happen to be lucky enough for the Hubble Space Telescope to have imaged this field some months prior. And you can see on the left, there isn't a dot where the arrow is. On the right, there is. So it's just as simple as that. When you write a discovery paper, you basically said, we looked, and it was here. So I want to go back and I want to emphasize the team that made this discovery. Okay, so you're going to hear from Enrico right after me. But there's Ryan, and you guys have seen his picture. Everyone else in that slide is a first or second year graduate student or a postdoc. I think that's remarkable. We had a 1-meter telescope. We didn't have a 4-meter telescope, right? I came into this program without a huge amount of, sort of experience, but I was able to make a significant impact coming into a department like Santa Cruz's. And I think the image that really typifies that is the fact that we got the breakthrough of the year. So to give some more details on that, I'm going to have Enrico come up to the stage and talk about what this means.